Okay, now we're going to talk about a slightly different notion. And this notion sometimes confuses people. It looks a little bit like mutual exclusivity, but it's not. We're talking about different types of things. If you have two events for which the probability of their intersection is the same thing as the probability of their product, you would say that the events are independent. Now this definition is like purely mathematical. When the events are not independent, then we say that they're dependent or that they're conditional. Remember some of the differences here. If you have A and B independent, what we have is that the probability of A intersection B is the product of the probabilities. If they're mutually exclusive, the probability of their intersection is 0. Right? In order for these events to be independent and mutually exclusive, we would need to have that the probability of the intersection would be, on the one hand, the product of A, the probability of A and the probability of B, and on the other hand, it should be equal to 0. What's the only way you can have a product of two numbers being equal to 0? That would mean that either the first is 0 or the second is 0. So the only way for two events to both be mutually exclusive and independent is if one or potentially both of them are the empty event. Let's see if we can make sense of this with an example. So you'll take a fair coin and you'll flip it twice. That's your random experiment. You're going to record the results of flipping a coin twice. There are 4 possible outcomes. Either you get 2 heads, heads and tails, tails and heads, tails and tails. So we'll have an event A, which will consist of the outcomes where you get a head on the first flip. So either heads heads or heads tail. And we'll look at event B. You get a head on the second flip. Head head or tail head. Now, as it happens, these events are not mutually exclusive. It is possible to get a head on the first flip and a head on the second flip. Right? In fact, we're seeing one of the 4 outcomes here that belongs to both events. So A and B are not mutually exclusive results, but they are also not exhaustive. There is a potential outcome of the experiment which is neither A or B. That's the outcome when you flip 2 tails. Right? So on the one hand, the full union is not the sample space and the intersection is not empty. We use the general addition rule. What's the probability of observing event A? Well, we wrote A as a union of 2 potential outcomes, head head, head tails. So that would be the probability of observing 2 heads plus the probability of observing a head and a tail minus the probability of observing simultaneously 2 heads and 1 head, first flip, and a tail on the second. Well, that is an empty set, right? The first set contains 1 outcome, head head. The second set contains 1 outcome, heads tails, and they're not part of the same set. These 2 sets are completely different, so their intersection is empty. Another way to put this, let's say that these were the 4 outcomes: head head, head tail, tail head, tail, we're looking at A as being the intersection of H plus HT, and we're further subdividing that into two things. We have HH and HT. Their intersection is empty. These two sets do not overlap. So the full probability of event A would be 1/2. You could have viewed it differently as well, just saying A consists of 2 of the potential 4 outcomes, and that probability is 50%, 1/2. You play the same game with event B, and you would get the probability of obtaining B is also 1/2. So if you look at the product of the probabilities of A and B, you'll get 1/2 times 1/2, and that's 1/4. But the intersection of A and B is not empty. It contains one of the potential outcomes, HH. The probability of the intersection then is also 1/4. One of the outcomes divided by 4 outcomes. The probability of the intersection is the product of the probabilities, and hence you conclude that A and B are independent. What this is saying, if you think about it, is that the probability of flipping heads on the first flip is independent from the probability of flipping a head on the second flip. These two events have nothing to do with one another. If you flipped heads on the first flip, that cannot affect whether you will flip a head on the second flip, if you have a fair coin. Let's imagine another situation. You have a 52 card deck. You shuffle it well, and you draw a card. We'll look at 2 events. The first event being that the card that you draw is an ace, and the second event would be the event that the card that you draw is a diamond. These 2 events are independent, right? There's 4 aces, so the probability of drawing an ace would be 4/52, 1/13, and there's 13 diamonds. So the probability of drawing a diamond would be 13/52, the 13 diamond outcomes divided by the 52 outcomes in total, so that's 1/4. The product of A and the probability of A and the probability of D is then 113 times 1/4 is 1/52. But that's exactly the probability of drawing the ace of diamond. Like the ace of diamond is the one card in your deck that is both an ace and a diamond. There's one outcome for an ace of diamond out of 52 outcomes, 52 cards, and that number is the same as the product. And so, because these 2 things are equal, A and D are independent events. Knowing that you drew an ace doesn't really affect the probability that you also drew a diamond, and vice versa. So imagine you have a 6-sided die and the numbers are 1, 2, 3, 4, 5, 6. But now the 6-sided die is not a fair die. It is loaded in such a way that the probability of getting one of the values when you roll the die is proportional to that value. And this could be done by, I don't know, like when you dig the holes, you don't dig as deep, and so some of the sides are heavier. So I don't know how you do it, but imagine a situation where that's the case. The question here is to find the probability that you would roll a 3 in this setup. It's unlikely to be 1/6. It could be, I mean, by accident it could occur, could be the case that the probability of rolling a 3 would be exactly 1/6. But in general, you're more likely to roll a 6 than you are to roll a 5, a 4, a 3, and a 2, than a 1 in that order. So you have a sample space of outcomes that hasn't changed. It's still 1, 2, 3, 4, 5, or 6. And what we know is that there's some constant V for which the probability of rolling K would be K times V. And that'd be true for all of the outcomes. Now, there's only 6 outcomes, and each of these is mutually exclusive. That's good to know. What you're seeing is that the probability of the full sample space, that's 1. The probability that you will roll a 1, a 2, a 3, a 4, a 5, or a 6 has to be equal to 1. It's good. And that's going to be equal to the probability of each of the outcomes. And since they're mutually exclusive, you can only roll a 1. If you've rolled a 1, you haven't also rolled a 3. Well, the intersection of all of these events is empty, so that the sum rule works here. The probability of the sample space is the sum of the probabilities of each of the rolls, which was what you would write right here. So this expression here in sigma notation, that's the sum of the probability of rolling a k, where k goes from 1 to 6. Now we know the expression for the probability of rolling a k, it's proportional to k. This would be equal to k times v. V is unaffected by what happens by k. We can bring it outside. We've done here, and you have the sum now. K is going from 1 to 6 times v. Or you can use a formula for the sum of consecutive integers, or you can also literally write it as v times 1 plus 2 plus 3 plus 4 plus 5 plus 6. You get 21v. So the full sum has to be 1, but you know that it's equal to 21 times a constant of proportionality, and so that constant of proportionality is 1 over 21. What's the probability of rolling a 3 in that case? Well, it is k times v, where k is equal to 3, so 3 times v, but we know what v is equal to. It's 1 over 21, so you get 3 over 21, which is the same as 1 over 7. So you see 1 over 6 wasn't that far off. But that's just an accident. The probability of rolling a 6 is much higher than 1 over 6. I'm assuming that you're familiar with this sigma notation. If you're not, let me remind you, when you write this expression, what you're really saying is that you're adding all of these terms where you let the index I here range successively, starting with j. The next one would be j plus 1, all the way up to the very last index that it could take, an. So that this expression here that we had, it is really saying you let k, the index, range from 1 to 6. That would be first p1 plus p2 plus all the way to p6. Let's go back to that dice, which was like strangely loaded. We'll roll it twice this time. And we assume that the second toss is independent of the first. You can imagine, if you want, that you really have 2 dice. They've both been loaded the same way. So what's the probability of first rolling a 3 and then afterwards rolling a 3 again? Well, if the second toss is independent of the first, you can look at the probability of the intersection of both of these things occurring as the product of each of them occurring separately. 1 over 7, 1 over 7, their product, that's 1 over 49. Does it make sense that the tosses would be independent if you're using the same dice? Probably not, right? Especially if the dice are loaded. So when we talk about using independent experiments or independent tosses, in your mind what you should think of is that we're using different objects. Well, here's an example which is perhaps a little morbid, but it would explain to you or show you how you would you could use independence as a tool to simplify your reasoning. The question is, which plane is more likely to crash? A 2-engine plane or a 3-engine? Now this question is actually fairly easy to answer if you assume that the engines fail independently. That's a convenient assumption to make, and we'll see why. Is it realistic? Well, we don't know. If engines are built in series, such that, one person who built an engine might also work on the next engine in the series and so forth, then it might not be realistic to assume that these engines would fail independently. Right? Say one of the engineers working on these wasn't as competent and they work on the same line. Well, whatever they worked on is more likely to fail. And so if one of them has failed and you know that both of the engines have been built by the same engineer, the fails are probably not independent. But we can assume that that hasn't happened. Or so, that the engines come from a big enough factory that when you build a plane, you don't necessarily take them one after the other in the production chain. Okay, so for the purposes of this exercise, we will assume that engines actually fail independently of one another. Another way in which this isn't actually realistic is what could be the reason why an engine failed? Perhaps a bird got caught in the engine. Well, if a bird got caught on this engine, there's a good chance that there was a swarm of birds and potentially the other engine could also have been affected. Again, we're going to assume that this isn't the case. P will be the probability that an engine can fail. And now you need to make another set of assumptions. How can a plane crash? What needs to happen for a plane to crash? If you have a 2-engine plane, we're going to assume that the plane can only crash if both engines fail. Now, the probability of one engine failing is P. The probability of the other engine failing is also P. And because both of these events are assumed to be independent, the probability of having engine 1 and engine 2 fail would be P times P, which is P squared. If you have a 3-engine plane, you'll assume that we will assume here that the plane crashes if any pair of engine fails, or if potentially all 3 of them fail. Again, if the failures are independent, in order to have a pair, exactly one pair of engines fail, you need to have 2 engines fail and one of them not fail. So you'll have the probability of one engine failing is P, another engine failing is P, and the other one not failing is 1 minus P. This would be, for instance, the probability of 1 failing, and 2 failing, and 3 not failing. There are many ways for a pair of engines to fail. In fact, it's a combination, right? We 3 choose 2. You're looking at pairs of engines that can fail out of 3 engines. It could be that you have engine 1 and 2. It could be that you have engine 1 and engine 3. And it could be that you have the last 2 engines. So 3 choose 2, 3 factorial divided by 3 minus 1 factorial, which is 2, times 3 minus 2 factorial, which is 1, and that gives you a total of 3. 3 ways in which a pair of engines can fail. If you have 3 engines A, B, C, you can have AB failing, AC failing, or BC failing. And what's the probability now of having all 3 engines fail? Well, if they all fail independently, that would be P to the 3, sorry. So your probability of at least having 2 engines failing would be the probability of 2 engines failing, which would be 3 times the probability of a pair failing in the 1-2 position. It could also be the 1-3 position and 2-3 position, so that's why you multiply by 3, plus the probability of all 3 engines failing simultaneously. So you end up with this expression here. So a 3-engine plane would have a probability of crashing of 3p squared minus 2p cubed, whereas a 2-engine plane would actually have a probability of failure of p squared, assuming that the assumptions that we've made are realistic. If you look at the chart here, for various values of p, and p has to go from 0 to 1, it looks as though the probability of failure for the 2-engine plane is smaller, always smaller. So a 2-engine plane would be safer than a 3-engine plane. That sort of makes sense if you think about it this way. In order for the plane to keep working, keep flying, a 2-engine plane needs 50% of its engines working, but the 3-engine plane needs 66% of its engines working. That's why it's less likely to be problematic if you fly a 2-engine plane than if you fly a 3-engine plane, even though 3-engine planes tend to be bigger and we tend to think of them as safer. Now, I'm not saying that the assumptions that I've laid out for you here are realistic assumptions, but they're not completely ridiculous assumptions. So you can have this argument all you want, but if you don't know what a realistic value of p could be, it's sort of a stupid argument to have. Like, if it's going to be the case that the probability of an engine failing is like super small, there isn't that much of a difference between the probability of failure for a 3-engine plane and a probability of failure for a 2-engine plane. And if the probability of failure is very high, then you're in cases where, yes, technically speaking, the 2-engine plane is safer than the 3-engine plane, but the 2-engine plane is, a 50% probability of failing. I'm not flying that plane, even if it's safer than the 3-engine plane. Let's look at another example here. Question of air traffic control. So it's a safety-related activity, right? You have a piece of equipment, and that piece of equipment is designed to the highest safety standards, whatever that would mean. And in many cases, you have duplicate equipment so that if one of them fails, or if a part fails, the other part can take over. At least you have redundancies in there. Now we'll look at London, and we're going to imagine a system which provides information from Heathrow to the terminal control at West Drayton. And now you have to decide whether you need to duplicate the system components. So this system that is going to be installed consists of a ground movements radar, a GMR at Heathrow, and that's combined with data from the National Airspace System, the NAS, and it sends the output to a display at the terminal control. So we're imagining that there's basically 3 components that could fail in here. GMR, NAS. Perhaps you run some experiments for all of these 3 systems, and you have a record of their failures, how often they fail. And presumably what we get is a way to estimate the experimental probability that they would fail, and you compute this experimental probability using 4 years worth of data. We're going to define the reliability of a system as 1 minus the probability of failure. In other words, it's the probability of it not failing. Now we'll assume that both the GMR system and the NAS system have reliabilities of 0.9999, 99.99%. That roughly speaking corresponds to one failure in 10,000 hours. So they tend to be fairly consistent, fairly reliable. And we're going to make the assumption here that the failure probabilities of each of these components, they're all independent from one another. So that is, if the NAS fails, it's not going to affect whether the GMR fails, or the new component also fails. So in the system that I've showed you, if you just add one new component here, so GMR, NAS, and the new component, everything combines into the display. If you just add one new component, the reliability of the single thread design, the STD, one new component, that would be the reliability of the GMR times the reliability of that new component times the reliability of the NAS, right? Because you're assuming that failure and success in each of the components is independent. If, on the other hand, you duplicate the new system, the new module that you're adding, then the reliability of the dual thread would be the reliability of the GMR times the reliability of the NAS. That hasn't changed, but now you need to compute the reliability of the new system, and you're going to have a failure if both of the duplicates fail. Looking for the probability of new 1 failing and new 2 failing, right? And that's not the reliability though. The reliability would be 1 minus that number. As it happens, the probability of N1 and N2 both failing, we write them separately here. We know what the probability of N1 failing, that would be 1 minus the reliability of the new system. Right, you just rearrange this expression here. And what's the probability of N1 and N2 failing? Well, it's the same one for N2, right? So what's the probability of both of them failing if they're independent? It would be the product of both of them, but they're the same, so that's the square, and there's nothing to worry about for the union here. Independent events, that's how you compute their intersection, the probability of their intersection, but that's not the reliability of the dual thread, that's the probability of the dual thread failing. So the reliability of the dual thread then would be 1 minus this. That's what you see showing up here. So the reliability of the single thread design is the reliability of the GMR times the reliability of that one component times the reliability of the NAS system, and the reliability of the dual thread would be the reliability of the GMR times the reliability of the NAS times the expression in the middle, which is the reliability of the dual thread. 1 minus the probability that both systems would fail. We also don't know what the reliability of the new module would be, because we don't have historical data. I said that we didn't know the reliability of the GMR and the NAS because in practice we don't actually need them to determine how much of an improvement in reliability we would have. Because the components are independent of one another. If you want to look at the improvement by you going to the dual thread instead of the single thread, let's look at the reliability of the dual thread divided by the reliability of the single thread. And you'll have this expression here. Now let's assume that the first component is not very reliable. Perhaps it only works 10% of the time. Then by going to the dual thread, you'd be like hugely increasing the reliability of the system as a whole. And if the first, or if the new component is very reliable, you don't have that much of an increase by going to the dual thread. So if you're not very sure about this new module, if it is unreliable, then there's a benefit in using the dual thread design. But you have to ask yourself why you would use a component whose reliability is not that great. But even if the reliability of the component, let's say like 99%, go into the dual thread would basically just give you a 1% increase in reliability. You would go from whatever you had as 100% now to 101%. That's not awesome. If it turns out that the new module is as reliable as the other two modules were, then the single thread has a combined reliability of basically 0.9997. That's 3 failures in 10,000 hours. And the dual thread would have a combined reliability of 0.9998. 2 failures in 10,000 hours. It doesn't seem like you would gain that much by having a dual thread. And if that component is expensive, well, you might actually procure savings for your group by just not installing a second component, not purchasing it. Independence is a bit easier to understand when you view it as conditional probability. It's a conditional probability of an event B given that some other event has occurred. That's a definition. That is one of the things you need to know in this course. The probability of B given A would be the probability of both events occurring, assuming that A has occurred. Now this only makes sense if A can actually happen. If the probability of A is greater than 0. If A can't happen, what's the probability of B given that A has happened? That's undefined. We don't know how to talk about this. Now if you look at the product of the probabilities for A and for B, let's assume it's not 0, so that both A and B can occur independently here. The probability of their intersection in this case, you can obtain it by taking the denominator here, P of A, and bringing it to the side. But you can also sort of view P of A intersection B as P of B intersection A. The order doesn't matter here. In the definition for the conditional probability, the order matters. However, and what we get is that the probability of A times the probability of B given A should be the same as the probability of B times the probability of A given B. No matter whether A and B are mutually exclusive or independent or what have you, as long as both A and B could occur. That's going to be an important result for us later. Let's put it in a square box here. We have a definition for independence, mind you. The definition for independence that we have is that the probability of A intersection B should be the same thing as the product of the probabilities of A and the probability of B. And so you'll have independence if it turns out, well, PA is equal to PA, that's great. If this component here, PB given A, is the same as P of B. If knowing whether A occurs or not doesn't change the probability that B occurred, then A and B are independent. Similarly, if knowing whether B occurred or not doesn't change the probability that A occurred, then A and B are independent. Imagine a situation where you have 100 people and you pick one of them at random. What's the probability that this person has high blood pressure? If you know nothing else about the population, this is an unconditional probability problem. We've looked at it before. It would be the number of individuals with the high blood pressure in the population divided by 100. When I say the population, I mean in the group here of 100. But if you start by filtering out all the people that have low cholesterol levels, and then you select one person, what's the probability that this person has high blood pressure? That's a conditional probability. The probability of having high blood pressure given that you have high cholesterol. The probability of selecting a person with high blood pressure given high cholesterol levels is probably different, or presumably different, from the probability of selecting a person with high blood pressure if we know that this person has low cholesterol. If there's a correlation, a link between cholesterol levels and blood pressure. Let's take a look at another example. Here we have a sample of about 250 people, and for each of these people we will test whether they have tuberculosis or not, TB, and we'll also test for their blood type. So we can subdivide the 249 individuals into 8 categories. Tuberculosis and blood type O, tuberculosis and blood type A, tuberculosis and blood type B, and tuberculosis and blood type AB, and then the same 4 blood types, but this time without tuberculosis. The numbers are given in this table right here, and you can also look at them by categories. There are 18 individuals of blood type AB, 55 of blood type B, 87 of blood type A, and 89 of blood type O. And you can also view them the other way. 113 individuals with tuberculosis, 136 without tuberculosis. The unconditional probability that if you pick a random individual in this data set and that they have TB, that would just be the number of cases where tuberculosis was found divided by the total number of people. And there were 113 cases of tuberculosis out of 249 cases as a whole. So that's 113 divided by 249, about 45%. But if you look at the proportion amongst individuals that have blood type B, you see that that number is actually above 50%, right? The conditional probability of having tuberculosis given that you have blood type B is actually going to be the number of cases where people have tuberculosis and blood type B divided by the number of cases where people have blood type B. 31 divided by 55. Or if you want, this is really 31 divided by 249 divided by 55 divided by 249. And here we're using the formula for conditional probabilities. So there's a 56% chance here of having tuberculosis if you are of blood type B. That certainly seems to indicate that there's a correlation between having tuberculosis and the blood type that we have. Right? In the population as a whole, about 45% of people have tuberculosis, but in the population of people of type B, at least in this data set, the proportion of those that have tuberculosis is substantially higher, about 11% higher. These variables unlikely to be independent. Well, here's another classic example. Assume that a family has 2 children and you're told that they're not twins. So there's a youngest kid and an older kid, or oldest kid. What's the probability that the youngest child is a girl if you know that at least one of the children is a girl? Here we'll assume that in this universe, boys and girls are equally likely to be born. I don't think that's quite the case in reality, but let's say it's a 50-50 split. Well, the naive solution would be to say, look, there's a 50-50 chance that the child will be a girl. So what's the probability that the youngest of these child is a girl? It's got to be 50%. And if that's what the question asked, you'd be right. But the question doesn't ask what's the probability that the youngest child is a girl. It asks what's the probability that the youngest child is a girl given that at least one of the children is a girl. That's a different question. We'll try to do it in a very formulaic way. We'll define the events. So A will be the event that the youngest child is a girl, and B will be the event that at least one child is a girl. Amongst the four different possibilities, you either have youngest is a girl, oldest is a girl, or youngest is a girl, oldest is a boy, or youngest is a boy, oldest is a boy, and youngest is a boy, oldest is a girl. Amongst these possibilities, there are two where the youngest child is a girl. Either you had two girls, in which case the youngest one had to be a girl, or you had a boy and a girl and the youngest one is a girl. So that's event A. For event B, you're looking at the outcomes where at least one of the kids is a girl. And there are three such outcomes. The only outcome that wouldn't be in event B would be the outcome where both kids were boys. Now if you look at this now, the intersection of events A and B is actually A alone. Right? B contains A in its entirety together with one extra option here. So what's the probability of A given B? What's the conditional probability of A given B? We just use the formula. It will be the probability that we have A and B divided by the probability of having B, which in this specific case is the same thing as the probability of A divided by the probability of B, because the intersection of A and B is indeed exactly equal to A. The probability of A is the number of outcomes in A divided by the total number of outcomes, 2 over 4. The probability of B would be the number of outcomes in B divided by the total number of outcomes, 3 over 4. 4's cancel out, left with 2/3. That's not 1/2. If you happen to know that at least one of the kids is a girl, well, the probability that the youngest one is a girl would be 2/3. You've changed the symmetry of the problem. And at the same time as you're doing this, you can identify that these two events are not independent, because the probability of the intersection of the events is not the same as the probability of A times the probability of B. And the probability of A intersection B happens to be just the probability of A in this specific problem, which is 2 over 4, 1/2. But then the probability of A times the probability of B, that's 1/2 times the probability of B. And unless the probability of B is 1, which it isn't here, we know it's 3/4. These two things cannot be equal. So saying that the youngest child is a girl and saying that at least one child is a girl, these are not statements that are completely independent. As events, they are dependent. And it makes sense. I mean, if at least one child is a girl, that presumably increases the probability that the youngest child is a girl, more than if you didn't know that bit of information. That leads us to the law of total probability. If you have two events, A and B, From set theory, what you can say is that the set B would be the intersection of A together with B, together with the intersection of everything that was not in A and B. Graphically speaking, what you should be seeing is that it's possible to recreate the set B given an event A by dividing the part of B which is in A and the part of B which is not in A. These are the only options that you have. When you write it this way, what you've managed to do is to split B into two mutually exclusive events. Now you can use the fourth axiom that tells you, because these events are exclusive, that the probability of B is the same as the probability of A intersection B plus the probability of the complement of A, everything which is not in A, intersection B. Now, if your event A was not either the empty set or the full sample space, so if it was a proper event, a proper subset, then the probability of A intersection B we can write as the product of the conditional probability of B given A times the probability of A. And that comes from the definition, right? The probability of B given A would be equal to the probability of B intersection A divided by probability of A, assuming that we're not dividing by 0 here, but we're not dividing by 0 because we've specified that the event was not the empty event. And it works the same way for the other one. The probability of B given the complement of A would be the probability of B intersection the complement of A divided by the probability of complement of A, and this thing here, that's 1 minus the probability of A, and that quotient, or that the thing by which we divide here is not 0 because we've assumed that A was not the full sample space, in which case the probability here is not 1, in which case 1 minus the probability is not 0, so this is well defined. So what we do is we rewrite the definition here so that we can isolate or solve for the probability of the intersection. And we're doing this because we would like to be able to go back here and the probability for B and to substitute expressions into these probabilities intersections. In general, what we get, this is actually quite intuitive when you think about it, the probability of something happening, probability of event B happening, would be the probability that B occurs, assuming that A occurs, times the probability that it occurred, plus, well, the probability that it would occur if A did not occur, times the probability that A did not occur. And you can generalize this in a very nice way. It doesn't have to be only an event A and its complement, as long as you find a set of K events, let's call them A1 to AK here, and that these events are mutually exclusive, so in a sense, none of them have a non-empty intersection. All of the intersections are empty, and they're exhaustive, which means that if you look at their full union, you have the original sample space. So if this is your full sample space, you can basically think of this as A1, A2, AK. Each one of them is disjoint with every other one, so they're mutually exclusive, and they cover up the entirety of the sample space S. But if that's the case, the law of total probability is simply the probability for event B, assuming event A had occurred, times the probability that it did occur, and you do this for every member of the set of mutually exclusive and exhaustive events. You can use the tuberculosis and blood type data to try to compute what the probability of having tuberculosis would be. Now we know how to compute this probability, and we have computed it. Right? You just count the number of cases with tuberculosis and you divide that by the full sample size, number of observations in the sample. Well, we'll see that we get the same result if we use a different formulation, in this case the law of total probability. The blood types actually give you a mutually exclusive partition of the population, right? If you look at all of your people, they either fall into the O blood type, A blood type, B blood type, or AB blood type. There's no fifth blood type out there, and every single person is in one of those. When you add them up, you actually get one. So that's the exhaustive part. The exclusive part is that, as I said, you have one and only one blood type. You cannot have two blood types simultaneously. So you can compute the probability of having tuberculosis given that you belong to any of the blood types. We've done it for one of them. We had computed previously the probability of having tuberculosis if your blood type is B, and that was 31/55. You do it for all 4 blood types by literally just dividing the number in the top row by the denominator, the number at the very bottom, the total number of people in each blood type. Now you use the law of total probability. What's the probability of having tuberculosis? That would be the probability of having tuberculosis if you're in blood type O, times the probability of being in blood type O, plus the probability of having tuberculosis if you're in blood type A, times the probability of being in blood type A, plus the probability of having tuberculosis if you're in blood type B, times the probability of being in blood type B, plus the probability of having tuberculosis if you have blood type AB, times the probability of having blood type AB. There are no other options out there. That's exhaustive. And then you can compute the expression by literally replacing each of these quantities from what we get in the data. And sure enough, you will get, if you sum up these things, a lot of these terms disappear here. And you put everything on what's already on the same common denominator. You just need to add up these numbers. 113 divided by 249, that is indeed 45%, which is what we had in the previous example.